This video was brought to you by Brilliant. Brilliant. Learn natural language processing in 6 easy steps. In this video, we're going to talk about markets and information. A market is just a place where people can trade stuff, and we're going to talk about two very specific kinds of markets: exogenous markets and endogenous markets. First, let's give some definitions. Exogenous markets are markets that are unaffected by the decisions players in the market make. Endogenous markets, on the other hand, are markets that will steer in a certain direction depending on the decisions made by players. Let's discuss exogenous markets. Prediction markets are a prime example. Prediction markets are markets for assets which have been created to aggregate individuals' predictions about a future event into a single group or opinion. The Iowa electronic markets, for example, are a place where individuals can buy or sell contracts that pay you in the event that a Democrat or Republican wins an election. So if you guys are confident in your predictions, be sure to bet on the next election cycle. Remember, friends, a gamble is not a gamble if you win. Another great example is horse racing, which we're going to use to illustrate how actors in the market behave and make decisions about betting. In horse racing, we can ask the question, how does a bettor who has W dollars available to bet allocate his wealth between bets on two horses? First, we make several assumptions about this model. The bettor will bet all of their money, W, on the two horses. We let R represent the fraction of his wealth he bets on horse A, and 1 minus R the fraction he bets on horse B. We let sigma sub A be the odds of horse A winning the race, and sigma sub B be the odds of horse B winning the race, i.e., if the odds of horse A winning are 1/3, then the bettor will win $3 for every $1 he bets on A. Easley and Kleinberg argue that with these assumptions in the betting model, there are only two key variables that affect a human's decision: the person's beliefs in which horse will win, and the person's risk tolerance / payoff matrix. First, let's talk about their beliefs. The bettor's choice of bet will depend on what the bettor believes about the likelihood of each horse winning the race, i.e., the bettor believes horse A wins with probability of A and that horse B wins with probability of 1 minus A. Additionally, if the bettor is right in his belief, then he will win an amount AW plus 1 minus AW, which can be greater than or less than the amount he started with. The bettor's choice depends on his expected payoff as well. We can model expected payoff with a utility function. We can model this idea by assuming that an individual has a logarithmic utility function, which means that utility grows at a decreasing rate as wealth increases. A linear utility function like UW equals W does not align with empirical evidence or common sense. Such a utility function would argue that an individual who is given the following gamble would be indifferent between accepting or rejecting the gamble. Suppose that a bettor's current total wealth is W and he has a chance of gaining W dollars with probability half and losing W dollars with probability half. The expected value is still W, i.e. 1/2 times 2W plus 1/2 times 0 is W. We would call this gamble fair. Intuitively, however, this is very strange because it implies that we value the certainty of W dollars the same as we value the chance that we win double or lose all our money. In fact, we know from real life that this is not the case. There was an entire book written about human decision making involving these principles called Thinking Fast and Slow by Daniel Kahneman, who showed that human utility functions indeed look more like a law curve. You can try this out yourself. The next time you lose money, ask your friend to play double or nothing. I'll bet the answer they give is emphatic no. This is the log diagram taken from the network's textbook describing a similar expected payoff curve. The utility of our wealth grows at a decreasing rate as wealth increases. Combining these ideas, we can create a utility equation that more accurately models human decision making in exogenous markets. This may look complicated, but in the common tongue, this means that our utility function is a factor of how likely we think one of the horses will win relative to another. A is the belief that horse A wins, R is the fraction of wealth we bet on horse A, and W is the total wealth that we are betting. Finally, sigma is the odds that are being placed on horse A. We can then break this down even further into the following system of equations. Using the log addition rules, we separate the log function into functions with the r term and functions without the r term. We do this because we are looking to maximize utility. We ignore all terms not containing r because r is the only thing we have control over when gambling. We can only control how much our bets are. We cannot control our wealth because we are betting it all, and we cannot control the odds or payoff factor on the horses. Thus, we can reduce our equation. If y'all think back to your Calculus 1 classes, we can maximize utility by taking the derivative and setting the derivation equal to 0. Solving for r, we get that it is equal to a, which is your belief that horse A wins. This equation means that in order to maximize your utility, you should just bet your belief system, i.e., go with your gut when you're betting. You have the Eiseley-Kleinberg-Bakhti guarantee. Disclaimer, this result only holds when we have a log utility function. Other utility functions may vary. Generalizability not included. Moving on to endogenous markets. Endogenous markets are markets where the decisions of participants affect the way the market is structured, the goods sold, and the price of goods. We ask the question, how does this happen? How do the decisions of players influence the market? We will use the example that won George Akerlof the Nobel Prize in Economics in 2001. This example is called Akerlof's lemons. There are several assumptions we make. First, there are two types of cars in the used car market, good cars and bad cars. Second, sellers and buyers value good cars at $10 and bad cars at $4. Finally, buyers cannot distinguish between good cars and bad cars, which implies asymmetric information in the market. Note that if there is symmetric information in the market, then the buyers and sellers will just end up buying and selling at a price of $10 for the good cars and a price of $4 for the bad cars, respectively. If anyone is wondering, the reason this thought experiment is called Akerlof's lemons is because cars that have a defect after they are bought are called lemons. When this happens, we have market failure. Let's assume that the fraction of good cars in the sale population is H. If you are a buyer and you have no idea whether what you buy will be good or bad, then you proportionally downweight what you are willing to pay for this car. You reason that you should pay $10 times H plus $4 times 1 minus H for the car, i.e., the probability of a good car multiplied by its respective cost added to the probability of getting a bad car multiplied by its cost. For example, let's say H equals 0.5. This means a buyer would only be willing to pay $7 for the car. If you're a seller, you now reason that it's no longer worth selling good cars because that is below your valuation. What happens ultimately is that there is a downward price pressure and an incentive to sell only bad cars. As a result, our good/bad car market has been reduced to just a bad car market. Now I know what you guys are thinking, but Dylan, how will I ever know that I'm buying a product that isn't utter garbage? Well, you won't. However, there are a number of solutions to address information asymmetries so that the probability of you buying a bad product decreases. Third-party certifications are an example. When you buy a used car nowadays, you will most likely find that many have the label Certified Pre-Owned as a way to signal that these cars are up to a certain standard and that warranties allow you to return or replace the vehicle if there is a defect. There are also reputation systems in marketplaces like Amazon where sellers that sell bad products are placed lower in the search queue relative to those with positive reviews. We see information asymmetries affecting the markets for goods, but what about something that is completely dissimilar, like international conflict? In conflict, a war is the result of information asymmetries. Both warring factions believe they are stronger than the other, and when the two groups fight, the relative strength of each other is revealed, addressing the information asymmetry. Similarly, when political leaders make public statements, they are tying their own hands because if they declare something and it turns out to be false, they suffer reputation costs. Constituents and voters are less likely to believe them if the information they disclose is bad information. This ensures that the marketplace of ideas is not filled with fallacious claims and leaders have an incentive not to dish out fake news. Or do they? All in all, the lesson here is that when life gives you a box of lemons, there was probably some sort of information asymmetry. Thank you for watching, and I hope that this video will encourage you to learn more about the world of markets and networks.